Good morning, everyone. So today we are going to deal with the topic of longitudinal wave. What we have done in the last week or so, so far our discussion was confined to what we call as transverse wave. And a typical model for transverse wave is a string connected. And what is transverse wave? In both longitudinal wave and transverse wave, we had dealt with mechanical wave. Mechanical wave means wave needs a medium particle to travel. In case of a string, the string particles were the medium which allows waves to travel on a string. We call it a transverse wave because if the wave travels in case of a string in x direction, wave travels means phase travels or waveform travels in x direction. The medium particles oscillate or medium particles undergo deflection in perpendicular direction, y direction. So here the direction in which the wave moves and direction in which the particle moves are mutually perpendicular. That's why I call it a transverse wave. Now we are going to deal with something and which is a typical example of longitudinal wave is a sound wave. We call it a longitudinal wave because in this case, the direction of motion of particle or direction of motion of oscillation of a particle same as the direction of motion of wave. Wave velocity and particle velocity are along the same axis. So if we take x-axis, if the wave moves along x-axis, the medium particles also oscillate or undergo motion along x-axis. And this is very common in case of, okay, so we'll deal with, in case of longitudinal transverse wave, we have taken a string. We take a similar model. And if you pay attention, those who understood derivation, again, for some of you, the derivation is not too important because questions are not much based on principles involved in derivation. But still, if you understand, it's good. And if you notice here, if you pay attention, you'll find this derivation is very similar to derivation of speed of the wave we had in case of transverse wave on a string. So let's take what is the model here. We can visualize the model as, let's just imagine there's a long cylindrical pipe. This is a cylindrical pipe. And within the pipe, there's a medium particle, which is air. It could be some other gas also. And one side we have kept a piston. Piston is like a surface. There's something similar to string kind of arrangement here. And this is a piston here. And how do we create oscillation in the medium particle and how do we create a wave? If suppose there we give a jerk kind of motion, here also what you can do, we can give a sudden jerk to the piston. We move the piston forward and pull it back. So this is something I'll kind of think if you this kind of motion, it will create a wave pulse. So when we move it right, what happens? So when we move it right, it pushes all the air particles also towards right. And when you push toward this right, it creates a kind of increases the pressure. And we pull it back, it comes back to the same state. So when we make this kind of motion here also, what we find, it creates a region of excess pressure. And excess pressure, it keeps moving along the length of the pipe. So there the displacement or pulse travels. Here the pressure pulse will get created. A sudden motion of piston will create variation in pressure. There it calculates delta y, it creates a delta p. It will create displacement also of medium particle, and the displacement will be in this direction. Okay, so it will create a motion oscillation in this manner. And if we keep oscillating this piston here, if we continuously keep oscillating, it will make the, if piston is oscillated in such a fashion, it will make the next air particle and then next one, that's next one. It will make all air particles which are within the tube to oscillate with same frequency as frequency of oscillation of this surface here, piston surface. This is a surface which is in contact with air. So there's similarity. So this is something the wave, the pulse gets created. Here also one jerk of the piston will create a pulse. And there we create a continuous wave by continuous oscillation of one end, which is the source end. Here also we can create oscillation by making this surface to vibrate. And just imagine if you think of something like a tabla and all also. What is tabla? Tabla also the surface oscillates. Even the microphone, what you use here also, if you look at the microphone also will have diaphragm kind of thing. It will have a surface and depending of frequency of sound which need to be created based on the song, and also this is actually the diaphragm or the surface oscillates at a particular frequency in a particular manner, and which makes air particles also oscillate. And if the surface is oscillating at one place, if listener at some place, there's also oscillation, air particles in between the source and the observer, which is human ear. And this air, all air particles is oscillate, and this oscillation reach our ear, and we have what you call as very sensory kind of small hairs, and in eardrum, those we sense those oscillation, and our mind converts those oscillation into sound mode. So there also this is an oscillation. This is what is typically happens. So let's try and understand some of the parameters related to wave. What are things we need to understand here? So first of all, I hope all of you notice the similarity. If you notice similarity between transverse wave and longitudinal wave, your understanding becomes easier. So what is the model we have taken? Model is, so this is the source end, and what is oscillated, piston is oscillated. And you understand here, what oscillation will make air particle oscillate? Oscillation of piston in this direction will make air particle oscillate, and this oscillation will travel in the same direction. So particle oscillation and wave motion is in the same direction. And if somehow we could oscillate a piston in this direction, if we oscillate piston in this direction, it will not create any wave. So transverse motion will not create any wave because fluids and air does not have shear resistance. So shear resistance is there only in case of solids. So solids only we can have transverse wave. We cannot have the liquid because of shear resistance. Okay, let's say how we calculate speed of wave. So if I create a small jerk here, the jerk here, that oscillation, assuming that there's no random motion, except for random motion, there's no systematic motion of air particle. We ignore random motion. Moment we create a jerk here, it makes, if we create a one plus oscillation, it makes adjoining air particle also to undergo similar kind of motion. And that kind of motion, it's transfer, it reaches different points. What is the speed at which the oscillation created at source travels along? That's what we need to find, speed of wave in fluid, which becomes the speed of sound also. Let's see how do we do that. In this case also, if you recall, in case of wave on a string, it's something like this, we're done like this, and after some time what we find, until a particular time it has reached up to this point, and after a little time later we find the shape of the string becomes something like this. So it means in delta t time it has moved a little distance, delta x, and delta x by delta t we calculate velocity. Something similar we do here. So when we here also what we have done in that case, if you recall, in case of transverse wave, if we apply a force, if the force acts at an angle, it makes this part of the string, every particle in the string, to move with the velocity, particle velocity. And this disturbance travels, which becomes the wave velocity. Something similar we do here. Let's go through that part now. So this is the piston here, and there's a pressure inside. Let's look at what are the parameters which are relevant here. Let the density of air be rho. This initial density is the pressure, and this is a piston here. Inside, outside, initially the pressures are equal. They'll be in the state of equilibrium. So what we do, let's, for a very brief period, we apply excess pressure. Excess pressure is when outside the pressure becomes not P, it becomes P plus delta P. So delta P into area becomes the net force acting. So moment we apply pressure, and what we have seen here, we have taken excess pressure is applied at T is equal to 0. And we observe what happens in time interval delta T. In time interval delta T, if we apply excess pressure, because of imbalanced force, the piston will move certain distance. The piston will move a distance equal to U into delta T, U being the velocity of the piston. U is the velocity of the piston. And what we find here in time delta T, earlier these are all air particles. We find in time delta T, this air molecules, not only here, even the air molecules up to this point have received the disturbance created by piston. It means wave has traveled up to this point in time delta T. This is your wave front. This is the extent which the wave has traveled in time delta T. So this is a figure we are going to use. And this figure also, we'll use the same expression. There also we calculated wave speed using impulse is equal to change in momentum. Here also we'll calculate impulse is equal to change in momentum. Extra pressure delta P, which moves the piston with the speed u. And there also what I'll assume, since the piston is moving at the speed u, so they're all air molecules which are present in the space where wave has traveled. This part of this air molecule wave has not traveled. This will not acquire speed. Wave has traveled only up to this point. So all air molecules present within the region where wave has traveled have acquired the same speed as speed of the piston. This is speed of piston is u. Let's calculate now what and what was the distance from here? What is this distance? So u into delta t is the distance moved by the piston. And in time delta t, wave has traveled. This distance is equal to v into delta t, which is velocity of wave into delta t. So this is point up to which wave has traveled. And this is the distance up to which piston has traveled. The speed of piston is u. All air particles which are within the region where wave has traveled will acquire velocity u. If you understood this one, let's apply this equation now. So mass contains the space between piston and section A acquires velocity u. So impulse is equal to change in momentum. What is impulse? Impulse is equal to net force into time. What is net force? Net force is delta P. If we take this volume, net force is delta P. Delta P into area, because delta P into area becomes force into delta T, becomes impulse. Now calculate what is the change in momentum. This entire air, which was all entire air molecule, which is within this space, initially the speed was 0. All of them acquire speed is equal to u. So change in momentum is this mass into u. What is this mass? Mass is equal to density into volume. So this is density. Volume is equal to AB delta T. What is volume here? Volume is area cross section A, and length is V delta T. This is the total length we are taking. So we are taking rho here because this is total. We are not taking this length here, because when we take this length here, here the density will not be rho. Density will change. So when we are taking the masses, we are taking this mass here, and this mass will be same. What is this mass is equal to? The density here and volume here. Both the density and volume are taken from initial state. So the rho into A into V delta T into U. Use the velocity acquired by entire mass of air present within this space. And what is delta P? We come to this term here. A delta T gets cancelled. What are we left with? Delta P is equal to rho into V into U. U is particle velocity, V is wave velocity. U is particle velocity and V is wave velocity. And now we'll see here what we do here, and what is excess pressure. We use the property of bulk modulus. If some of you recall what is bulk modulus equal to, bulk modulus we have done. Bulk modulus formula is something like this. And let's try and understand what does bulk modulus mean. This bulk modulus is, see, any object if we take, if we exert pressure, under pressure the volume of any object changes, be it solid or be it liquid. So this bulk modulus relates change in pressure with the fractional change in volume, and that ratio is called bulk modulus. And just to understand here also, if we take something like if we take something like cotton and we take a piece of steel, both cases if we apply equal change in pressure, we know the cotton will change in volume, fractional change in volume of cotton will be more. So this is more compressible like cotton. If fractional change of volume is more, bulk modulus is less. Those material which are not easy to deform with pressure will have higher bulk modulus. And which material has highest bulk modulus? The one which just deforms the least. Among the material which has very high bulk modulus is diamond. And you can easily understand why diamond has high bulk modulus. And what will be the bulk modulus of gas? Will the bulk modulus of gas be small or large? Deep, what do you think? Bulk modulus of a gas vis-a-vis solid or liquid. Suppose we have one solid and we have one gas. Between the two, which will have higher bulk modulus?
The gas will have very low bulk modulus.
Very low bulk modulus. Very good. So that will have lower. So we understand, and this is a relationship here. This equation has delta P. So what we do delta P here, delta P also we substitute in form of bulk modulus. This B into delta V by V. Okay. And let's understand here what is delta V. V is the original volume and this is the change in volume. So where is the original volume and where is the change in volume? Let's identify where is original volume, where is the change in volume here. In this figure, see, during this time interval delta t, this was the initial volume. We are not concerned with the part which is unaffected by wave. And this is become my final volume. So can we write those expression? The area of cross section into this length is initial volume, and area of cross section into the length is my final volume. Let's substitute those terms here and we get our relationship. It is B into what is change in volume. Change in volume is so much. This is the change in volume. This was the initial volume, final volume. This is the change in volume, U into delta T into area of cross section. And what are the initial volume? Initial volume is this total length. Total length is V delta T. This expression we get here. And which is the, this is the, you notice here, U term gets cancelled. And what is the U term? U term was the speed of the piston. And V is the speed of the wave. What is the expression we get? We get expression V is equal to root of B by rho. It is bulk modulus by density of fluid or gas. This is valid for all three shapes. It is valid for solid, liquid, as well as gas. So this is something, so those who have not followed this much also, all we need to do, if you don't follow also, I'll not stress too much on very good understanding of this derivation, because derivation doesn't help you solve many numericals. If you understand is good, make a little more effort to understand. If it is not very clear also, don't bother. What we need to do is understand this expression here. Velocity of longitudinal wave is this expression. So what we'll do, we'll try and understand this expression better and understand longitudinal wave also a little bit more. So this is expression bulk modulus. How do we calculate bulk modulus for a gas? See, typically we deal with longitudinal wave. A typical example of longitudinal wave is sound wave. And sound wave is something we come across every day or every moment. That's why sound wave is important, and sound wave travels in air. So this formula, longitudinal wave, is valid for solid, liquid, as well as gas. But let's look at gas first. Gas is, when we talk about gas or air, we are talking about speed at which sound travels. So we'll take a subset of this application. Let's take it in case of velocity of sound in ideal gas. Though it is valid for all cases, let's deal with ideal gas. So in case of this, derivation was done several centuries back. And for calculation of this, what this is formula, V is equal to root of B by rho. And Newton, I think what, 300 years back also, whatever. So he said this is derivation, and based on the derivation, let's find out critical speed of sound in air. How do we calculate B? Bulk modulus. We said, okay, bulk modulus we can calculate assuming air to be an ideal gas. And ideal gas, what is the equation? V is equal to nRT. That's the ideal gas equation. And he assumed whenever sound travels, he assumed the process to be isothermal. He assumed the air temperature is not changing. So we can assume the process to be isothermal. Based on the isothermal, he calculated P. What does isothermal process mean? Isothermal process means P into V is a constant. If P is into V is equal to constant, it basically means if we write in derivative form, fractional change, delta P plus V plus delta V by V is equal to 0. Or it gives me what is bulk modulus. From this expression, can we find the value of bulk modulus? Bulk modulus is minus dP divided by dV by V. So from here, we can easily find what is the bulk modulus for ideal gas under isothermal process. What is the bulk modulus here? If we substitute this one, we find the bulk modulus comes equal to the pressure. So pressure of the gas is equal to bulk modulus, which means higher the pressure is, higher is the bulk modulus. More difficult to compress it. So and we substituted okay, and pressure. So this is something once we arrive at the bulk modulus, the density of air also is known, and he calculated the speed of sound using this formula, pressure by rho. And he found the theoretical calculation was not matching with the experimental observation of the speed. So this is something, there was some flaw. It was theoretical derivation based on what assumption we made, it was not matching. And then it was correction made by Laplace correction. What is Laplace correction made? Laplace correction said, no, there's wrong assumption that as sound wave travels in air, It undergoes change in pressure and other things. Pressure changes. And whenever this process takes place, the process is not isothermal, process is adiabatic. Why is adiabatic? If you recall adiabatic, any process which happens very quickly. In case of sound, when it travels, also change in pressure is very quick. If the frequency is 100, it means pressure, so many oscillation of pressure happens, which implies the change in pressure happens in extremely short period of time. And whenever time periods of any process very quick, it's not isothermal, it does not allow time for its heat transfer to take place. Hence, the process has to be treated as adiabatic. So that's a Laplace correction. He assumed the process to be adiabatic. And there's sound reason also why should be taken as adiabatic. So when we have adiabatic, this is the process. PV raised to power gamma is equal to constant. And when we have PV raised to power gamma is constant, if we write in terms of fractional changes part, this can be written as dP by P plus gamma dV by V is equal to 0. And from here, again, if you substitute the value of dV by V in this equation and dP in this equation B, the value of bulk modulus comes equal to gamma into P. For adiabatic process, bulk modulus is gamma into P. So he substituted this value in above formula. And when he substituted this value, it came almost exactly matching with actual speed of sound in air, and they tested in other mediums also it valid. So gamma P by rho, what is gamma P? Gamma P is bulk modulus for adiabatic process. And for ideal gas, this can also be written as, using PV is equal to nRT, it can also be written as gamma RT by M. Because you know PV is equal to nRT, can also be written as PV is equal to nRT by V, and this also number of moles, mass of the sample by NAV, and it can also be written as okay. So this is basically same equation. So it is two forms. It is written as gamma P by rho, and this very simple manipulation gamma RT by M. So any of these two equations. That's what the speed of sound is, gamma RT, and this is very commonly we use. We use this word more than gamma P. This is a term which is more commonly used formula for speed of. And this is valid not only for air. If in place of air we use some other medium also, it is valid. Gamma RT by M. Let's see in case of what is M value for air. What does M indicate here? M indicate molar mass. And molar mass has to be in what? With M is equal to molar mass, it has to be into kg. See, typically in case of air is predominantly a mixture of, okay, so in case of air, mean molar mass of dry air comes to 30 grams per mole. Okay, 30 grams per mole is value of M. And density of air, or we can calculate from the density also. Air density of air at normal temperature is something about 1.2 kg per meter cube. So from this formula also we can calculate velocity and speed. You can substitute pressure. Pressure is equal to atmospheric pressure is roughly 10 to the power 5. What is the gamma I should substitute in this case here? Anyone can tell what is the gamma here? Here, what is the value of gamma I should take? Here is what? Gamma depends on monatomic, diatomic, or polyatomic. What is air composition?
Diatomic.
Diatomic. So we have to take gamma for diatomic. What is diatomic gamma value? What is value of gamma for diatomic gas?
5/2.
Huh? How do we calculate gamma? Do you recall how do we calculate gamma? Gamma is equal to Cp by Cv. What is Cv equal to? Anybody recalls what is Cv equal to in terms of R?
5/2 R.
Okay, basically F by 2 R, and for diatomic gas degree of freedom is 5, and Cp is Cv plus R. So Cv is Cp plus, it becomes equal to 7 R by 2. Hence gamma for diatomic gas is 7 by 5. And if it was monatomic gas, degree of freedom would have been 3. So basically we can substitute. And when we calculate at different temperature, at 0 degrees, as per the calculation, speed of sound at 0 degree comes to, we just substitute the values, comes to 331 meter per second. which matches with the actual observation. And as the temperature changes, what we notice here, velocity is proportional to the square root of temperature. And this temperature has to be in Kelvin. As the temperature increases, the speed also increases. At 20 degrees centigrade, we take the speed to be 340 meter per second. And 20 degrees centigrade is normal, close to the normal air temperature. So whenever nothing is mentioned, we take the speed of sound to be 340 meter per second. What are the factors which affect the speed of sound in a gas? What does M depend on? M depend on, does it make sense? Molecular composition. What does molecular composition means? A gas could be a single gas or it could be a combination of multiple gases. If it is a combination of multiple gases, where we have to take the weighted average of molar mass. How do we take weighted average of molar mass? N1 M1 plus N2 M2 divided by whatever numbers are present here. So while M depends on how many gases are present and what is the relative proportion of different gases. As this proportion changes, M value will change. And if the gas is a mix of monatomic and diatomic, gamma also may change. So molecular composition affects both gamma as well as M. And for similar example, suppose we take example, say suppose we take a pipe. In one pipe, it is filled up with helium, and other pipe also is it's not normal hydrogen gas. It is a deuterium isotope of hydrogen. Why we are taking deuterium isotope? If we have deuterium isotope, it will have same molecular mass is same as helium. So when we had two gases here, M value will be same for both. This also M value is 4 grams per mole. And if it is a hydrogen gas, which is a molecule, so two deuterium compounds compound, this also will have a molar mass of 4. Both of them are same at the same temperature. But still the speed of sound in helium and this deuterium hydrogen gas will not be equal. Why would that not be equal? The M is equal, yes, gamma is not equal. In case of helium, it is monatomic. In monatomic, gamma value is what? Gamma value is 5/3. In diatomic, gamma value is 7/5. Okay. Hence, this gamma is more. And because of gamma being higher, the speed of sound in helium will be higher. This is gamma effect. Effect of adiabatic constant. So if this formula here, so basically if we have any composition of any mix of gas is given, to find the speed of sound in any mix of gas, we need to calculate value of M here and gamma here. And this is a simple calculation. We'll take up some examples. You'll find it easy to figure it out. It's simple formula use. The application of this formula is fairly simple. We'll look at some examples and they're pretty straightforward. So what are factors affecting the speed of sound? So if I ask the question, it's a gamma P by rho. If I ask this question, do you think the pressure will affect the speed of sound? Does pressure affect the speed of sound at a given temperature? So suppose we change the pressure. You know, whenever there's a low pressure area, whenever before we talk about, I think recently I've seen the rains and all, there's low pressure area. So the pressure at a particular place undergoes change. So when the pressure changes, temperature remaining same, also the pressure may change. When the pressure changes, does it also change speed of sound? This formula is here. But if temperature remains constant, wherever pressure increases, gamma also, rho also, density also will increase. So temperature remaining constant under constant temperature condition, any increase in pressure leads to proportionate increase in density, and this ratio remains constant. Thus, pressure alone does not affect speed. What affects speed is temperature. The factors affecting speed of sound for a given gas molecule, if a molecular composition is fixed, speed depends on. So if we are not changing the mix of what proportion is nitrogen, what proportion is oxygen, what proportion is hydrogen, if the mix is not changed, so if mix is not changed, gamma will not change, M will not change. Only thing which change will T. Hence, speed depends on temperature only, and it increases by about 0.6 meter per second per degree centigrade. Can we calculate this expression? Suppose I ask you, how do we find out for 1 degree change in temperature, what will be the change in speed? Can we calculate this one? Can we prove this value? How do you find out this expression? What will be change in speed for unit change in temperature? From this expression, can we find it out? V is equal to root of gamma RT by. Which two things are changing here? We are changing only one parameter. Other composition of gas is not changing. So T is getting changed. And when T changes, V also is changed. And both changes are small. How do we write expression whenever small changes are involved? If V is changing, the fractional change in speed, which is equal to dV is the change in speed and V is the original speed. What is this equal to? dV by V is equal to what? Kaushik? What is dV by V equal to? Pritam,
Yes, sir.
can you tell me what is dV by V equal to? This expression, we have done it number of times. Whenever we have relationship between quantities, these are related quantities. Which two quantities are changing? Only V is changing and T is changing. For again gas, what you're saying, if the temperature of the air changes, the mix of composition of air is not changing. Hence, gamma is not changing, M is not changing. Only T is changing. What will be, this indicates fractional change in V. It will be related to fractional change in temperature. Power of what will the expression should be? Can you tell me what should come on the right hand side? No? What is power of T here? And this, okay, some of you still recall, this is something, this is exponent into dt by t. This expression. So what is change? If I have to calculate what is change in velocity when change in temperature is equal to 1 degree centigrade, let me put these values. What would dV be equal to? dV will be equal to 1 by 2 into change in temperature, which is 1 degree. And what is the initial temperature? Initial temperature, we have to always use, this is in Kelvin. Initial temperature, if we take, see, suppose I take initial temperature at what? Air temperature, if I take 27 degrees centigrade. So this value will be, I can, for approximation, I'm taking this is 300. And velocity of speed is something 340. How much this comes to? This comes to roughly 2.6 meter per second. So every 1 degree centigrade increase in temperature, roughly the speed of sound increases by 0.6 meter per second. And this is something how we could have arrived at that expression. Okay. And this I already mentioned, at a given temperature, change in pressure will have proportionate change in density, has no effect on speed.
So,
Yes.
so but this value of change in speed, it'll vary for different temperatures, right, sir?
Yes, correct. But will the effect be significant? That's why I said within a temperature range, it will come into this like this. When we talk about air temperature does not vary over great range. Okay, so this, of course,
Yes.
what will happen here? If I calculate dV with respect to initial temperature being 0, it would have been 320. If I calculate at 20 degree, it becomes 340. The rest of them remain same. Okay. So there will be some variation. This is a very approximation. And why I took up this example, just to give an idea, every degree centigrade, what is the effect on speed? It will be in this range, depending on what was the initial temperature. Of course, it will depend on the initial temperature, but more or less in this range. What does change of composition mean? Change of composition means, suppose we change the composition. How is the composition changed? When we change the composition, the value of M will change. If we replace air molecules with a heavier molecule, M will increase. If we replace with lighter molecules, M may decrease. So depending on what kind of other molecules are replaced with, the value of M will change. Okay. And what is the natural change which happens? All of you know humidity. What does humidity mean? If we say humidity is 0%, it means there are no, if we take any small volume of air, it will not contain any molecules of H2O. Okay. And mix of air, we have mentioned earlier also, weighted average M for air is about 28. Okay. What happens? What is the molar mass of H2O? Molar mass is 18. So if if water molecules are added, or some of the air molecules are replaced by water molecule, what will happen to M? Will it increase or decrease? So when humidity increases, increase in humidity means we are adding molecules of water, H2O, which are lighter. If they are lighter, value of M decreases slightly. Change is not big, change is small. As M decreases, the speed of sound increases. So compared to dry air, humid air has slightly higher speed. And what is the effect of that? Very slight. So humidity, if compared to 0% humidity, when humidity becomes 100%, speed increases by about 1.5 meter per second. So very small effect of humidity. Humidity effect is because increased humidity implies increase in addition of water molecules which are lighter compared to weighted average molar mass of air. That is 28 and this is only 18. That's why it slightly increases. Decreases with altitude. Why should it decrease with altitude? So as from sea level, as we keep going up, as we go up, the temperature drops. As the temperature drop also, the speed also become lesser. So if we take layers of air from surface, if we take different layers, as we keep going up, the speed here, this is speed is higher, and here as you go up, speed becomes lower. So in terms of if we talk about which is this denser or this is denser, lower speed means this medium at higher altitude is more dense. And this is rarer medium. So when we talk about any medium, how do we decide whenever we compare two mediums for the purpose of calculation of speed of wave? How do we define between two medium which is rarer and which is denser? Whichever medium speed is higher is called rarer medium, and whichever is V is higher called rarer medium. Wherever speed is lower is called V is lower is called denser medium. So in this case, actually, some of you may recall refraction. So in this case, what happened whenever the sound travels, if you just apply Snell's law, any sound which is created because of change in temperature, as we keep going up, velocity keeps decreasing. If we create sound waves tend to bend upwards. I'm not going to detail. So some of you apply Snell law, you'll find the sound wave tends to become bent upward if at a higher altitude temperature keeps dropping. And so what is the effect of this? So if you create a sound here, if another person is at a long distance, the sound which should have reached here, because of bending, sound bending like this, the person here will not be able to hear the sound with as much clarity as you could have heard had this kind of bending effect not been there. And if you read history, there's one particular case where this had played a very important role. It creates a kind of acoustic shadow. Is this understood? Virup, have you following what I'm saying now?
Yes, sir.
You understand why this sound bends? Which principle?
It's traveling from rarer to denser medium.
Rarer to denser. Yes, we have seen the Snell law. And it keeps bending rather than going straight. A significant proportion of sound it bends upward. So what happened? The sound which has created it should have reached here also. Lesser thing will reach. And you know what happened in case of if you one very famous example of this bending was in case of U.S. Civil War. In U.S. Civil War, so what is something like this? There was there was some army at one place, and there was another battalion of army which was at a distance of not very far, maybe some tens of miles. And there's one contingent of army was here. There was another contingent of army here. And what happened? The war broke out here. When the war breaks out, what happens? You can see cannon shots and all. So this war broke out. It created all cannon shots and all. And because of that particular time, the temperature gradient was so much. And because of acoustic shadow, there one more contingent which was available at some miles away. Because of acoustic shadow, they could not hear the sound of war in form of cannon shots fired or gunshots fired, and they could not come to their rescue. Had this acoustic shadow not been there, they would have heard this, yes, there's a war going on, a war has started, they could have come to their rescue. So something simpler things also may have a major bearing on how things go. Okay, so it creates bending. So this is something there. So what are we doing now here? So far, yes, Vignesh.
So the refraction of wave, like we did in transverse waves, is not applicable here.
See, what we talk about, see, why this, okay, why we said here, this is rarer medium and this is denser medium. Okay, how we arrive denser, rarer, denser, I hope this is understood. And upper is denser medium. So if the sound wave travels like this, which way it will go? It tends to bend towards normal when it goes from rare to denser medium. It will bend like this. That's what is happening here.
Yes, sir. Like, can there be any reflection also?
Yes, there can be. It has similar property. It can have reflection as well.
Yes, sir.
Okay. Similar principle. This is something acoustics do. So we're just talking about effect of altitude, and this is a nice example. And this is something, some of the things, how scientific or how natural phenomena played an important role in history. Also, is something one can understand. So what are we dealing so far? We were talking about longitudinal wave. I hope we understood what does longitudinal wave mean. Oscillation in the same direction as the wave travels. And we have only dealt one thing. If you have not understood anything, what is V equal to? B is equal to B by rho. That's what we have done so far. And when we calculate B, when it travels in gaseous medium, how do we calculate B? We calculate bulk modulus for not isothermal process, we calculate for adiabatic process. And when we calculate for adiabatic process, what is B is equal to? B is equal to gamma times pressure. And at a constant temperature, this ratio remains constant. And P by gamma can also be using ideal gas equation. It can also be written in this form. That's the only thing we have done here. And sometimes when it is a mix of gas, we have to calculate the weighted average value. We have to calculate weighted average gamma value also, which we see in some cases. These calculations are again mathematical manipulation, which will come to that later. So what we have so far we have done, this is speed. We are trying to understand what factors affect the speed of sound. What are factors which affect? Gas composition affects speed. Pressure does not affect if the temperature remains same. And temperature also affects, and humidity also affects. Reason humidity affects because it changes the composition of medium. Humidity means increase in humidity implies addition of some molecules, gas molecules, which are lighter in molecular weights are lower, and lower value of m increases speed of sound in that medium. Okay. Same thing if would longitudinal wave travel in solid? Let's understand what a solid mean. Let's understand what a solid mean. Suppose we have a block of solid, which could be steel block or anything. So how do we create a longitudinal wave? If a person is standing here, if you this is okay, this could be even a thin rod also. I think more appropriate example is thin rod. Suppose we have a thin rod. If we strike this rod from here, we hit the rod like this. It is equivalent to trying to move this surface towards right. So if we strike the rod like this, it will create a longitudinal wave. It will try to compress this particular section of the rod. It is something similar to moving the piston, what we had discussed earlier here. So if we have a thin rod, if I have a tuning fork, which is vibrating like this, one tuning fork, if I bring in contact with the rod, it will create a longitudinal wave in the metallic rod. And when it travels here, we have taken in case of bulk modulus for ideal gas is equal to gamma times pressure. What is the bulk modulus for a thin rod? Bulk modulus for a thin rod is taken as Young modulus. Why Young modulus is taken as bulk modulus for thin rod? What happens if it is the rod is not thin, it's a block? In case of three-dimensional solid, it is more complex and it creates a different kind of wave. We will not deal with that. It is more complex. There's a shear wave as well as transverse wave. What happens in case of this is one way we can create oscillation longitudinal wave. Just is it possible to create even transverse wave in case of a thin rod? Yes, we can create a transverse wave. In case of transverse wave, what I need to do, rather than making this end of the rod oscillate like this, I need to make it oscillate like this. How do I create a transverse? I strike this rod in this direction. It will start vibrating like this. Or if I have a tuning fork, if I tuning fork like this and bring in contact with the rod here, it will start oscillating like this. When it start oscillating like this, in this case, it is Young's modulus. It is compression, and it is trying to compress and relax. In this case, it is like shear modulus. But if you recall shear, so in this case, wave travels like this. In case of transverse wave traveling on a thin rod, we will not take Young's modulus, we will take the shear modulus. So in case of solid objects, both longitudinal waves also possible and transverse wave possible, and which happens in case of earthquake. In case of earthquake is what is actually what do you understand by earthquake? Earthquake also, you would have heard of something like earth surface also, like several large plates. If we have a large metallic plate and which has some thickness also, and and suddenly they're all connected, and suddenly what happens, suddenly because of pressure, suddenly there's sudden motion in some point. Basically the two plates suddenly slip. Anything suddenly slip, it creates a vibration wherever it happens. Whenever any such slip takes place in tectonic plates and all, it creates vibration at whichever place it happens, and that's called epicenter. But this is like a solid, it is three-dimensional object. And when it has vibration can happen both. It can have vibration, it creates vibration like this also. And it creates vibration like this. And this vibration, when it starts traveling, this travels as a longitudinal vibration, and this travels as a transverse vibration. For longitudinal vibration, I take Y value. For transverse vibration, we take G value. And G value is always smaller than Y. So what happens? The transverse wave travels at a slower speed, and longitudinal travels with a higher speed. So what will happen? The person standing here, will have two types of earthquake. First, one earthquake will strike this point at a certain distance, because this wave will travel faster. So one kind of vibration will strike first, and a little time later, second type of wave also will strike. So the fact that we get two kind of oscillation hitting a place whenever earthquake takes place is an example of transverse wave as well as longitudinal wave, which can be created in a three-dimensional solid object. Okay. So far, something has gone into the head.